Hi all, welcome to the online lecture for the course EE302 Electromagnetics. In this lecture, we will be discussing topics from Module 5. The topics that will be discussed are Pointing vector and Pointing theorem, power flow in a coaxial cable, and complex average Pointing vector. This is the first half of Module 5. Before listening to this lecture, I would suggest that you just go through the first post, that is the first link that I have shared in the Google Classroom. It's a link from slideplayer.com, and the name that I've given for the link is Introduction to Electromagnetic Waves. So if you watch that link, you will basically get an idea about what a wave is, how a wave propagates, and how do you find the equation for a wave. So once you hear that lecture or once you see that video, then you come back and listen to this lecture. Okay. So here we're starting with pointing vector and pointing theorem. Now basically in module 5, we're discussing about time varying fields and the interaction of electric and magnetic fields. Okay, like actually right from the second half of the fourth module, we've started discussing about time varying fields, and that's how we derived the Maxwell's equations in final form. So when an electric and a magnetic field interacts, okay, it results in an electromagnetic wave. And as we all know, when an electromagnetic wave propagates from one point to another point, there is some amount of energy that is transported. Okay? That is, energy can be transported from one point where the transmitter is located to another point where you have the receiver by means of electromagnetic waves. And the rate of such energy transportation that is obtained by Maxwell's equations. And it is this rate, that is the power that is flowing over a period of time. An expression for that, that is what pointing theorem gives you. Okay, pointing theorem mainly deals with the energy flowing in an electromagnetic wave. So in order to derive the pointing vector, we're starting with Maxwell's equations. So as you can see, given by equation 10.58a and 10.58b. So these are, if you see, these equations we've already derived in the fourth module, and these equations are for time varying fields. Del cross E is equal to minus dou B by dou T. That is what we've derived. And if you replace the B as mu into H, you can write it in this form as given here. Similarly, del cross H is equal to J plus dou D by dou T. That is what we have derived. The J, the conduction current density, is written as sigma E. This again we have derived. And your D here in dou D by dou T, if you replace the D as epsilon into E, then the equation can be written as shown in 10.58b. So the derivation starts with these two Maxwell's equations. Now, when you dot both sides of equation 10.58b with E, then the equation becomes E dot del cross H is equal to sigma E square plus E dot epsilon dou E by dou T. And this particular expression here, this identity that you see over here, del dot A cross B is equal to B dot del cross A minus A dot del cross B. This identity I've already given to you when we've done the vector review. So we are not going into the derivation. Okay. You just need to know this identity. And we are applying this identity over here by substituting the vector A. Supposing I take my vector field A as H and the vector field B as E. When you substitute that and into this identity, okay, and then I'm applying that into equation 10.59. So what I'm going to get is H dot del cross E plus del dot H cross E is equal to this right hand side. So what I've actually done here is when you substitute A as equal to H and B as equal to E, the first term in the identity, that is B dot del cross A, what does that become? That becomes E dot del cross H. So that is the same as the left hand side of equation 10.59. Okay, so that is on the left hand side, and the other two equations in the identity will add up, and that's how I'm replacing the left hand side of equation 10.59 to form the new equation 10.60. Similarly, when I dot equation 10.58a with h on both sides, that's how I get equation 10.61. And this term h dot del cross E is equal to minus mu by 2 dou by dou t of h square. I'm going to substitute it into 10.60. And that's how I get the last equation that is shown on this slide. Most of these equations, I believe, are self-explanatory. If you can just write down these equations, whatever is written on the PPT will be clear. So that's how we get the last equation. Now, what we're doing is, the last equation that you've just written on the previous slide, we're just rearranging the terms a little so that the del dot E cross H term is written on the left hand side, and then throughout the equation I'm going to apply the volume integral on both the sides. So I get equation 10.62, and what I'm going to do is this left hand side of equation 10.62, which corresponds to a volume integral. Okay, I'm going to, in using the divergence theorem, which relates the volume integral and the surface integral, I can write the left hand side as equation 10.63. You should not be having any confusion in this at this point, because we've already done a lot of derivations and a lot of problems related with divergence theorem. So now what you see is this equation here 10.63, the terms in this equation, okay, the physical interpretation is as given below. The left hand side, surface integral of E cross H dot ds. This actually gives you the total power which is leaving the volume. The first term on the right hand side corresponds to the rate of decrease in energy stored in electric and magnetic fields. That is, half epsilon E square corresponds to the rate of decrease in the stored electrical energy, and similarly half mu H square, this stands for the energy stored in the magnetic field. And the second term on the right hand side corresponds to the ohmic power dissipation. So this equation 10.63 is very important, and this equation is actually referred to as the Poynting theorem. So equation 10.63 is referred to as the Poynting theorem, and I've already explained the physical interpretation of the various terms involved in the equation. So now the term E cross H, or the quantity E cross H on the left hand side of the equation, that particular quantity is referred to as what you call the Poynting vector. It's denoted by a P, and the unit of Poynting vector is watts per meter square. And this particular expression, it actually represents the instantaneous power density that is associated with the electromagnetic field at a given point. So if you want to find out the net power that is flowing out of a given surface, you just need to integrate the Poynting vector. So the Poynting vector is associated with the power density, and if you integrate it over a closed surface, that will give you the net power that is flowing out of the surface. Okay, so now that we've derived the equation corresponding to Poynting theorem, and we've also defined what you mean by the Poynting vector, we are coming to the statement of Poynting theorem. So Poynting theorem states that the net power which is flowing out of a given volume V, it is equal to the time rate of decrease in the energy stored within the volume minus the conduction losses. Conduction losses corresponds to the ohmic losses itself. So I believe that particular statement is self-explanatory, and you're supposed to know the statement of Poynting's theorem. Now that we know that your P is a Poynting vector, which means associated, that is P will definitely have a magnitude which corresponds to the net power. In addition to that, it should also have a direction because it is a vector. So how do you determine the direction of Poynting vector? That means the direction of the power flow. How do you determine that? That is the next part. So if you see P is equal to E cross H, so what does that imply? The direction of the Poynting vector should be normal to the plane containing E and H. Okay, so as per our convention, the convention that we're going to use, we're going to consider that your electric field is propagating in the x direction, okay, and the magnetic field H is propagating in the y direction. So what does that imply? The electric and the magnetic field are mutually perpendicular to each other, and the direction of propagation of the wave, the electromagnetic wave, that is going to be in the z direction. That means, in effect, the direction of E, H, and the direction of wave propagation. These three quantities are going to be mutually perpendicular to each other at any point of time. And we should remember that the Poynting vector will be in the same direction as that of the wave propagation. So if E is along the x direction and H is along the y direction, P is going to be along the z direction. Okay, and AK, the notation that we're using for the direction of wave propagation is AK, that is equal to AE cross AH, direction of electric field cross direction of magnetic field. An illustration of the Poynting theorem is as shown in the figure. So what is the theorem? The theorem, it deals with the power flow. Okay, so you have power in and power out of a given surface. And what are the various sources of power that is present within, that is responsible, that is your power, you have a power in and a power out. Okay, so the power out is reduced mainly because of the rate of decrease of energy which is stored in the magnetic field and the electric field. So those two quantities are shown in the figure, and another reduction is from the ohmic losses. So the power balance for electromagnetic fields, okay, in a figure form, it is illustrated as shown in this figure. Now, the link that I've attached here, the YouTube link, please copy paste that into your web browser. It's an animation of how an electromagnetic wave moves. So you can actually see that is how E and H are mutually perpendicular to each other. And when they vary with respect to time, you will have your wave propagation in a third direction, which is mutually perpendicular to both E and H. This concept will be clear once you watch that particular animation for an electromagnetic wave. So please copy paste that link and watch the animation for propagation of an electromagnetic wave. So this slide here deals with something that I've already explained. If the proper direction of E is along the x direction and H is along the y direction, the direction of P is going to be along the z direction. When you write E cross H, the magnitude is going to be EXHY and the direction is AX cross AY. What does AX cross AY give you? It gives you AZ. So PZ corresponds to the magnitude and AZ is the direction of power. Now that we have derived the expression for the Poynting vector and we've also stated the Poynting theorem, the next part is to derive expressions for instantaneous Poynting vector, the time average instantaneous Poynting vector, and the total average power. Okay, and these three terms comes under the basic concept of complex Poynting vector. Okay, so in order to derive these terms, we are starting with, see, E of zt. Why I write it as zt is the electric field is varying, plus the propagation is in the z direction. The wave propagation is in the z direction. Okay, that's why it's written as E of zt. But at the end, you will find an ax. That is because the electric field itself, it moves or it varies in the x direction. So the expression is E0 e raised to minus alpha z. See, this alpha has a particular meaning that we'll be discussing later in the 6th module. For now, you just understand that E0 e raised to minus alpha z, that part represents the maximum value. And then you have cos omega t minus beta z ax. So essentially what you have to understand is an electron, any variation, okay, any time harmonic field, okay, is normally represented as a sine function or a cosine function. Now in this case, we have used the cosine function representation. So the expression for E is written. Now the expression for H. So In place of h0, we have actually written e0 divided by eta, and then again you have e raised to minus alpha z as in the previous case. So eta is a term that is defined as intrinsic impedance. This again will be discussed a little later, okay? When we start with dealing with electromagnetic waves and the wave equations, we'll be discussing about intrinsic impedance. For now, what you have to understand is intrinsic impedance is actually the ratio of E by H, E divided by H. So actually, what was I supposed to write over there? The term that should have come over there is H0, isn't it? H0 e raised to minus alpha z. That is what gives you the maximum value for magnetic field. In place of H0, I have written it as E0 divided by eta. So if eta is equal to E0 by H0, that is definition. By definition, the intrinsic impedance is equal to E0 by H0. So from that, I can write H0 as E0 divided by eta. So that is how I get this expression. And then cos omega t minus beta z minus theta and kind of a shift. Okay, AY. So these are the expressions for E and H. So how do I find? See, P of ZT, this is the expression for the instantaneous Poynting vector. When you write E cross H, what happens is the magnitudes are just getting multiplied. So I get E0 square divided by eta, e raised to minus 2 alpha z. And then the cos terms of both E and Z are written down. And the direction AX cross AY, that is going to give you AZ. So that is how you get this expression. Now, how can you simplify cos A? So this is actually of the form cos A cos B. And what is cos A cos B equal to? It is equal to 1 by 2 cos A minus B plus cos A plus B. So I'm substituting that particular expression here as 1 by 2 cos A minus B plus cos A plus B. And when I substitute, I'll get this expression, the last expression that is shown on this slide. So as I mentioned, once you substitute the cos A cos B form into the equation for P of ZT, the resulting equation that we got in the previous slide, the last equation in the previous slide, that represents the instantaneous Poynting vector. Now, for more practical purposes, okay, it is useful to determine the time average Poynting vector. So if you see, the time average Poynting vector is represented as shown in equation 10.67. So the form is P average of Z. And I'm sure you're familiar with this equation. It is obtained as 1 by T integral 0 to T P of ZT dt, where P of ZT represents the instantaneous Poynting vector. So if you're integrating it over the period T, the resulting equation that you get corresponds to the time average Poynting vector. Now, an important thing that you can note here is this time average Poynting vector has another form as shown in equation 10.68. The time average Poynting vector, another way of expressing it is 1 by 2 real part of ES cross HS star. So star actually represents the complex conjugate form of the magnetic field. Now, this relation, that is how the time average Poynting vector can be equated to half real part of E of S into H of S star. This derivation, I've left it as a self-study. The solution for this derivation is available. See, I have already shared the solution of all unsolved problems in the textbook by Sadhgu. So, in that folder, if you go to chapter 9, see, please remember, I have taken down, see, these equations are basically from the Sadhgu text itself, okay, but this is the older edition, that is, these equations are taken from the 3rd edition. In the 4th edition, if any of you are following the 4th edition of the textbook, okay, these equations come in chapter 9, the electromagnetic wave propagation chapter. All these equations about Poynting vector is from chapter 9, and the unsolved problem at the back of chapter 9, 9.44. Please note, problem 9.44. That problem gives you the derivation of how the time average Poynting vector can be equated to 1 by 2 real part of E of S into E of S cross H of S star. Okay, so I request you to please go through that solution and understand that. Now, continuing with our explanation. So if you apply this equation 10.67 by substituting the expression for P of ZT, which we have obtained, and if you integrate it within the limits 0 to t, where t is substituted as 2 pi by omega, okay, you can just interpret and try it out. The final answer that you're going to get is as shown in equation 10.69. So this equation 10.69, what does it give us? It gives the time average Poynting vector in watts per meter square. So far we've discussed the expression for the complex instantaneous Poynting vector, which is given by P of ZT, and also the time average instantaneous Poynting vector, P average of Z. Now, if you want to find the total time average power which is crossing a given surface S, that is given by equation 10.70. That is, you integrate, it will be a surface integral, the time average, the instantaneous time average, that is what is given as P average, that dot ds. This is going to give you the total time average power. So if you see, there are three terms that we've discussed with regard to a Poynting vector. Instantaneous Poynting vector, which is represented as P or P of ZT. Then the time average instantaneous Poynting vector, which is given by P average, and also the total time average power, which is given just as P average. So please note the way in which your P is written. P written in the italics form, that gives you the P varying in italics form gives you the instantaneous Poynting vector, and the P in normal form gives you the total time average power. So this P here, so the main thing is here, we need to understand what the difference between the three Poynting vectors are. So if you see P in italics x, y, z, t, that is the one that we derived using the E cross H expression. That gives you the Poynting vector. It is the instantaneous Poynting vector. The unit is in watts per meter square and it is time varying. The next P average, which we obtained by integrating 1 by t integral 0 to t P of zt dt. There, that is again the Poynting vector, but it is the time average Poynting vector. The unit is in watts per meter square. So it is a vector, but it is time invariant. And then finally, the P average, the total average power that we find using equation 10.70, that it actually gives you the magnitude of the power that is crossing a given surface. Okay, so it is a scalar quantity, and the unit of that total average power is given in watts. So all these three forms for the complex Poynting vector, the instantaneous form, the time average instantaneous form, and the total time average power in watts, the scalar form, these three terms are important. So far we've discussed about, we started with the Poynting theorem, deriving the Poynting vector. We came to the Poynting theorem, the statement for the Poynting theorem, and the different forms of the Poynting vector are also discussed, instantaneous form and the average form. The next topic is to find the power flow in a coaxial cable. That is, we're going to use the expression that we just derived, the Poynting vector expression P is E cross H. Using that equation, how can you determine the power flow in a coaxial cable? That is the next topic. Okay, so I'm sure now by now all of you are familiar with what a coaxial cable is. It has an inner conductor. So in this case, the inner conductor has a radius small a. The outer conductor has a radius small b. A DC voltage is applied between the conductors, and the steady current which is flowing through the inner and the outer conductor, that is given by capital I. Okay, and So this is how the cable is set up. So now we need to find out the power flow in the coaxial cable using the equation P is E cross H, and then we'll be integrating that Poynting vector to find the total power. So that means we need to find an expression for E and an expression for H. So to find the expression for H, we are going to use Ampere's law, which we've been discussing a number of times. The line integral of H dot dl is equal to the current enclosed. This is the expression for Ampere's law. And in this case, this dl, that is the path that you're considering, the Amperian path, it is going to be a circular path because the configuration that we're considering is a coaxial cable. And the circumference of the path is going to be equal to 2 pi r. So substituting h dot 2 pi r is equal to I, or the expression for h is given as I divided by 2 pi r for a less than r less than b. So the expression for h is obtained. Now to find the expression for E. See, this is an expression that we have already derived earlier in module 2. The E due to an infinitely long conductor is given by, in this case, lambda divided by 2 pi epsilon r. Okay, so the r is the distance from the conductor to the point of interest, if you remember, and lambda is your charge density. See, the same equation we have derived earlier, only thing in the second module, the charge density, the notation that we were using is rho L, if you remember. So the expression for E was rho L divided by 2 pi epsilon rho. Now here in this case, instead of rho L, the notation that we are using for charge density is lambda, that's all. But the equation remains the same. And the potential difference between the conductors, okay, that is given by equation 2, lambda by 2 pi epsilon ln b by a. See, this equation also, that is the potential difference for a coaxial cable, that is, if you use the equation V is minus integral E dot dl, when you apply that equation, this is the expression that you get for potential. Okay. Now, writing E, that is the field, the expression for electric field, I'm going to write it in terms of the potential. So, to write E in terms of V from 1 and 2, E can be written as follows. So writing E in terms of V, this is the expression that you get for E. E is equal to V divided by ln of B by A into R. So now the power density, that is your instantaneous Poynting vector expression, the power density P is E cross H. So we know that the expression for E cross H will be the magnitude of E into the magnitude of H into sine of the angle between E and H. And I've already mentioned that at any point of time, E and H are always mutually perpendicular to each other, which means you get sine 90. So your P can be written as just magnitude of E into magnitude of H. So the expression that you obtained for E, that is substituted I'm sorry, and the expression that you obtained for H, I by 2 pi r, that is also obtained. So when you substitute, this is the expression that you're getting for P. So now we have obtained the equation for the power density. Now how can we find out the total power across any cross section? To find the total power, we have to integrate the power density over the cross-sectional surface. So in this case, your ds, that is your, and we are actually integrating P dot ds. The ds in this case, it is going to be 2 pi r dr. Okay, so in order to find out the total power, we are integrating. The limits are, lower limit is small a and the upper limit is small b. And I'm substituting the expression for P. And for ds, I'm going to write 2 pi r dr. Once again, I'm repeating what am I actually integrating? The expression is the total power is equal to integral of P ds. Okay. And then once I do the integration and substitute the upper and the lower limits, the resulting equation is the equation that I have to find out. That is the total power that is flowing in the coaxial cable. So as I mentioned, once you integrate and apply the limits, the final expression that we get for the total power flow along the cable, it's going to be VI. That means the product of the voltage V, the DC voltage which is applied across the conductors, and I is the current that is flowing in the inner and the outer conductor. So W is equal to V into I, and this is the final expression for power flow along the cable. So with this, I'm winding up this particular lecture. So let me just review whatever I've discussed in this lecture. See, in this lecture, we have discussed the first three topics related with Module 5. That is almost half of Module 5 is actually over. Please go and look up your syllabus. The topics on Poynting vector and Poynting theorem, power flow in a coaxial cable, and complex average Poynting vector. These three topics I have covered in today's lecture. Okay, so please listen to this lecture, and these notes, please take it down in your notebook. Okay, and consider this lecture to be equivalent to a regular class that I'm offering to you. Now, I'll be sharing the next lecture soon, and in that lecture, we'll start with electromagnetic waves, which is the next half of Module 5. Okay, thank you.